So, good morning, everybody. We are only half of the participants now, but I think it's time to start. I hope you had a very good day yesterday. I think we had very interesting talks and very nice discussion. And now I'm going to go through the agenda for today. So we are going to start with two presentations that are related to experiences with remote sensing devices. First, Thomas Schmidt from DLR, and he will present on short-term solar forecasting from sky imaging. And then Ines Würth will present some results about how the measurement range of long-range lidars is influenced by meteorological conditions. And after that, we will have our World Cafe. And therefore, I hope that you have done your homework. So as we told you yesterday, you should be thinking of what you want to discuss today. And the idea of this World Cafe is that we will split into groups, and we will, so each person should attend one of these 4 different stations that we will explain later. And we will have discussions on how to mitigate barriers, or how possible solutions for each of these stations. But Ines will explain it later, or I will explain it later. And we are gonna skip the break that is supposed to be at 10:30. So the idea is that we will start with the World Cafe at 10, and we will continue until 11:15. And if you need to take a coffee, just go and pick it. And after that, we will all sit together, and we will present the results from each group, and we will have a discussion on that. And the idea is the end to find a way of summarize our results, and maybe decide on how are we gonna proceed with the results of the workshop. And if you want to add anything, this is the time now. Any comment? No? So then I think we can already start with the presentation. So Thomas, please. Yes. Ah, okay. But you can...
Yeah. So, good morning. Okay, I don't think I have to introduce myself. I did it yesterday. I'm really glad to be being invited to this workshop, and hope to present you this morning a little bit of introduction in short-term forecasting for solar energy, and based on sky imaging technology. I would like to give a little bit of motivation and applications, methodology, technology, and also a little bit of insight in our current research. Before I start, let me introduce a little bit of introduction in traditional or general solar forecasting. You might be familiar with that. It looks quite similar to wind energy forecasting, but just to give an overview. Here we see we mainly have 3 different information sources, starting with, for sure, on-site data from PV power measurement. We can use this for persistence forecasts or any other time series modeling. Then we have the satellite images. They're quite helpful. They have, here in Europe, a resolution of 1 by 1 kilometer, above the equator. Time resolution of 15 minutes per image. We can use cloud motion vector methods or any other cloud tracking method to track the clouds, to extrapolate, and to have nowcast of cloud situation in the next minutes, hours. And then for sure we're using numerical weather prediction models for next couple of hours, next day, and so on. On top the PV simulation, we get our PV power predictions. To give you an idea of the performance, I have two graphics here from single-site forecasting. On the left-hand side, we see two typical diurnal cycles of PV power, here normalized, and with 50-minute average values. We see numerical weather predictions follow the trend quite well, but for sure resolution is not that high, so the variability is underestimated and some deviations still occur. With the cloud motion vector method, this is here a short-term forecast, I think 50-minute ahead or 1 hour ahead. We are quite closer to the observations, and also the variability is much higher, so closer to the observations. On the right-hand side, some aerometrics. As far as I have seen yesterday, looks also similar to what we have in wind energy. From the first minutes up to an hour, persistence works quite well. Cloud motion vector method for 50 minutes, 30 minutes ahead, then outperforms the persistence, and after a couple of hours, 3, 4, 5 hours, usually the numerical weather prediction model outperforms or have lower RMSE than the satellite image-based method, which is clear. With satellite images, we only have a snapshot of the current situation, clouds developing quite fast, so just tracking or nowcasting after a couple of hours, then you lose the performance. And also we have then, after a couple of hours, we have the night, and in the night or for the next day, this does not work anymore. And which is also a common practice, is using a combination of all different information sources. I have seen that yesterday for wind energy as well. If you do so, this is a multiple linear regression with different weighting for the different forecast horizons. You see that you can reduce the RMSE for all the forecast horizons again. But what is clear, this is 50-minute average. This is, let's say, short-term forecast, 50-minute ahead, 1 hour ahead, and a day ahead. When we are interested in higher resolution, we have to look on minute temporal resolution, or even second temporal resolution of a second. And then you see that solar irradiance has a much higher fluctuation on these temporal scales, which is not visible if you have 50-minute averages, as you can see here. Magenta and the light blue is 1 hertz or 1 second and minute resolution. If you look on how clouds look like, which are the main impact on PV power intermittency on this short-term period, for sure we do not talk about day-night circle or seasonal circles. We talk about 50-minute variability, then clouds are the main impact. We see here Google Earth snapshot with a single cumulus cloud, or a single cloud with a dimension of maybe 100 meters. You see a solar field beneath. You see also a few wind turbines here on the right-hand side. Gives you an impression of the size, what is possible with clouds, and also about the complexity with cloud edges and its structure. So if you want to predict or even analyze or monitor solar irradiance, surface solar irradiance with a higher temporal resolution, the traditional methods like the weather models and also the satellite images with 1 by 1 kilometer resolution, this is not enough to get these structures. So we are using ground-based sky imaging. That means we put a camera on the ground that looks into the sky, and with the fisheye lens we are able to have a high resolution for cloud monitoring. You see 8 different sky types with the main cloud conditions we can have. The clear sky case, an overcast situation with stratus clouds, rain clouds or thunderstorm clouds, and then also these high heterogeneous clouds, cumulus, altocumulus, and so on, where you can see the that the high resolution is needed, and you can imagine what kind of fluctuations these kinds of clouds produce on the ground. So where can we use it for, and what can it be used for? This looks also quite similar to what we have at wind energy. We can use it first for single plants, a large-scale PV, concentrated solar power, or PV diesel in off-grid situation. So where we predict, or where we want to use the system for a single solar system, but also can be used for connected systems where we predict for single different ones. For what it's used for sure, operation control of the plants, for the grid management, storage management, trading, can also be used for demand side management in the short term. Okay, then let's go over to technology and methodology. This is just an insight of what the full range of it's only a short introduction in what is there at the moment. We have to say that, or I have to say, sky imaging technology is developed for a couple of years now. There are different groups developing hardware and software, and I can only now give some impression of what I did in my PhD thesis and a little bit of what other groups did. In hardware, we see here 3 commercially available industrial sky images. On left-hand side from a company from Australia here, from CMS Schrader in Austria, distributed by Echo Instruments. This camera here from Statistical in France. They look all similar. They have this camera on top under a glass dome with the fisheye lens. They are mostly in a housing with ventilation and heating, a small PC for communication and maybe a little bit of processing of the images. Then there is another category, I would say, or I would call it the low-cost category. Here's a system developed by my colleagues in Almeria from Solar Research Institute and CSP Services. They're using a Mobotics Q25. This is a commercially available surveillance camera. Costs below 1,000 euros. Usually used in this way. Here they use it the other way around to monitor the sky. And now you maybe have an impression about the hardware used. Now let's go over to methodology, to the software. This is a workflow I used in my thesis. Some steps from the raw image to a final product, an irradiance forecast. And we mostly start with the segmentation of the image, discriminating sky and clouds. Then you have to do image projection. We have the fisheye projection, rectify the image. Then cloud and cloud shadow projection. So we only see the clouds in the sky, but we want to have the position and also location of the shadows on the ground. This is needed for our forecast. Then we need an irradiance modeling to come from this information where the shadows are to a surface solar irradiance distribution using real-time measurements on site and clear sky models. And then with analysis of the cloud motion, we can do the forecast. Here an illustration about this, how the segmentation looks like. I used a simple binary approach. You can use in an RGB image the red to blue color ratio. This enhances the contrast, and you can apply a simple threshold. In the end, you have the histogram. You want to divide the image in sky and clouds. There are some issues, for example, with the bright sun here, the pixels are saturated. I had a method to overcome this a little bit at least. Here you see then the histogram, you see quite much more contrast. And so the image in the end can look like this. In the next step, an illustration about cloud shadow projection, how it is done. So you have the sky image on the ground. You see in a certain angle from the center of the image the cloud. Now you need the additional information about the cloud's height above ground to retrieve its position in the sky. Together with the sun position, you can project its shadow on the ground. And here I want to illustrate what happens if you have a wrong cloud height, for example 500 meters wrong estimation. Then you would expect it to be in a different height, means also in a different position, and in the end you would have a mislocation on the ground, leading to phase errors, timing errors, and so on. Cloud motion is done with different techniques possible. We use optical flow, tracking the cloud edges. In the end, I used then a frozen advection scheme, extrapolating what is seen now into the future with a constant cloud motion. Some notes about the measurement range, because we want to talk about it later as well, which is coupled with the forecast horizon. We have to say this is quite variable because it depends on the cloud height. You can imagine the lower the clouds are, you cannot see that far. So the clouds at the horizon of the image or the edge of the image are not so far away then. If the clouds are lower, then compared to cirrus clouds with a cloud height of 9 kilometers, for example, then for sure the cloud movement. Speed is important, but also direction. If you predict for a location, for example, in the southwest of your camera and clouds coming from southwest, we have seen it yesterday in Laurent's presentation. This has an important contribution here, and viewing angle, so the part of the image you are using. To give you a number, in Oldenburg we found out in 50% of all cases we have a forecast horizon of 15 minutes. Some challenges most of the groups are facing in terms of software. For sure, we have always a complex, or we have often complex cloud situations with multiple layers. So clouds hiding behind others because we only have a single perspective. Cloud development, 3D clouds, then clouds at the edge of the image where we get perspective errors because we see them from the side. Then really challenging is cloud transmission. We need what we need for the radiance modeling. We see different colors of the cloud, but what we want to have is the opacity or the transmissivity of the clouds and its interaction with the solar rays. On the hardware side, for sure, droplets and dew disturbing the image quality, birds disturbing the image quality, and then what you have seen in the previous images is the bright sunspot region. So these problems are tackled by different groups, but I think they have not been all overcome. Here, a time lapse, sorry for a little bit of noise, how a cloud shadow projection then can look like. This image is analyzed here in a binary cloud sky, is projected here on the city of Oldenburg. You see a little bit of the coverage and the development of the cloud shadows and how they move from northwest, from north to south across Oldenburg. So some words on the performance of the sky imaging system. So I did several applications of camera-based forecasting, present some results here. Here we did experiment on multiple site forecasting with 25 minute ahead forecast. We had one single camera. Around here you see almost 100 stations here. That was pyranometer stations measuring with 1 Hertz the solar irradiance. It's distributed above around 5 by 5 kilometers from the camera. You see the shadow projection in the dark gray color. This is shadow, and then here the clear parts corresponding to the clear sky here. And in color, The color indicates the irradiance values, in red high values and in blue low values. And here we see that the projection here with a cloud height of 2,200 meters works quite well in this situation where we have a clear, clear and sky segmentation. Works quite well. In the lower part, you see a forecast for a single station with time series also of measurements. This is the station above here, and this line presents the forecast path. So clouds were moving from south to north. We are predicting a clear sky part a couple of minutes ahead. This is illustrated here with a red curve. And what can be seen here, that timing is okay. We see this ramp up and the ramp down. We have some problems with calibration for sure, and the amplitude, a little bit timing errors. But here we use the resolution of 1 second. So I think I think it's an 8-minute ahead, and it was 12:05, and the ramp down was 12:18, so 5 to 12 minutes. This forecast was here working quite well. Another study we did on this ramp forecasting for the PV diesel hybrid system, there the idea was to see if we are able to predict cloud occurrences, so the ramp down events, after a clear sky period. So we have a period of at least 10 minutes of clear sky where we are sure that our PV generators work well, and then cloud occurs and variability starts, or intermittency. And here in blue you see this were binary forecasts where we predicted the irradiance below a certain threshold, and in blue you see true negatives. That means here we could predict a couple of minutes ahead the ramp down events quite well, here in this situation, here as well, and here again. Another performance slide showing forecast RMSE with forecast horizon for different cloud conditions. Here I separated all analyzed conditions, or discriminated into 7 different cloud types you have seen on one of the first slides, just to illustrate how large the variety in forecast performance is under different sky conditions. Here with lowest RMSE, these are the persistent conditions with clear sky, overcast. For sure, there's not much happening in the 25 minutes. RMSE is low, and therefore also the skill is low, so we cannot beat persistence. The highest RMSE occurs with cumulus, stratocumulus, altocumulus clouds. And here, for example, if you look at the blues, stratocumulus, we also can outperform persistence forecast. Okay, some words about current research. What we are planning to do in Oldenburg in this year is to set up a measurement network with cameras in the distribution grid of EWE, is the DSO in this region, with 34 cameras, as I said, and we want to distribute them more or less regular in the rural area, and want to have a higher density of cameras in the city of Oldenburg. Here, this is a close-up of the city of Oldenburg. The Trafo region is marked with, in this line. This is also more or less the outline of the city. Here we want to put about 10 to 12 cameras, and the blue circles indicate for defined cloud height the coverage. Just to illustrate that we have here overlapping regions, we can use this for multi-camera systems, where we can retrieve then 3D clouds, because we see clouds from different perspectives, and also want to cover the whole city, because in the end the objective is to simulate the PV production from all single PV plants in Oldenburg, the rooftop plants as well as the large plants on the field. Additionally, it's not only the cameras we want to equip with the stations, it's also some meteo instruments, focus on irradiance measurements, also temperature and humidity, and we also think about wind speed measurements. But yeah, we put them on rooftops. We are not sure if this is worth to do because the location is maybe not so suitable. Okay, thank you for your attention. I hope there's a little bit of time left for questions.
Test, test.
Hi, I have a question about how do you measure the cloud height?
There are several methods available. First of all, there are ceilometers working like similar as a Lidar. It's a Lidar system pointing vertical in the sky, and you can have a point measurement of the current cloud height. This is an expensive information source, but groups are working on methods working with the cameras, maybe two cameras, triangulate the clouds you see in the image is one option, or using one camera, one pyranometer with some cross correlation. So different indirect methods available or in development to get this information.
And which method did you use?
What I have shown here, this were ceilometer measurements, so direct point measurements, where we had this information. And yeah, this is also mostly used as a reference because it's, I think, the most exact information we can have.
Thank you.
I have a question about how did you classify all of the periods? Was that some network that you set up, or was it done by hand?
The different sky conditions?
Yes.
This was an automatic machine learning algorithm where we first sorted the situations manually and then trained the algorithm that we have an automatic classification of each situation. And we only used the dominant, where we had the dominant sky condition and not a mixed type.
I have also a question. What do you think, could you extract the wind speed actually from your cloud movements? So if we're going back to forecasting here for wind ramp events, or if the Lidar doesn't work, maybe is that feasible?
Good point. I discussed that not often with colleagues, but I did, and I got this idea yesterday again. We have to find out. We have to correlate what we see in the images with Lidar measurements, with mass measurements, with other information. I'm not sure.
I think the challenge that we have is that we don't have measurements that far up. So you couldn't, I'm not sure if it helps if you correlate it with mid-mass measurements, because it's so very different. Yeah.
In principle, this should be possible from our experience, but the problem is that you only have very local measurements, and distortions from the fisheye optics is you also have to take into account. For when you want to look to cloud motions, there maybe it's better to use Meteosat second generation. They have 15 minutes image interval, and there's also a product from Humidity available about cloud motion vector, even for different cloud heights.
Just a comment to this wind speed. I don't think that wind speeds in 1-2 kilometers height are really relevant for wind power. The numerical models are also quite good at that height with respect to the wind speed, because there is no disturbance from the ground So what makes it challenging to predict the wind is really the ground, right? So, so up in that height and extrapolating down, or that's done in the numerical models anyway. So I don't think this is, and we don't have clouds in, we have fog in, that is also a challenge for the solar power, but not really the clouds.
Yes, I agree. I don't think that you can extract wind speed. So really, wind speed at hub height or.
But I don't think it's a necessary measurement.
Yeah. But what we heard yesterday, maybe is cold fronts or special events where you see
I think
clouds arriving.
Value in detecting events.
Yeah.
That's probably more what I was going at. I don't expect to use it as a measure of wind speed. I expect to use it as a measure that there is a weather event coming and use that in the machine learning algorithm.
Mike, wanted to say something?
Yeah, I'd like to ask, probably coming back to what we were talking about before, but the centimeters, are they scanning centimeters or are they just points? And I mean, it would seem fairly obvious to get the centimeter to do some scanning.
Oh, point measurements. You can tilt them, but usually they're used vertical.
But wouldn't it be a fairly simple addition to just put the centimeter on some sort of tan and scan and tilt head and get the centimeter to look at the sky? And then you have a very detailed and very sophisticated picture of the clouds and also of the particles. So it's not just the cloud, but it's how much the radiance will also be attenuated on the way in.
Yeah, for sure. Good point. I think so. So we have temporal resolution can also be a couple of seconds. It's measuring up to 15 kilometers, the instrument we have. So if you scan, you can have more information, yes, for sure, for 3D clouds. But up to now, they are usually used statically and not moving or not scanning.
I have a question with respect to bringing this forward. I know in Germany there is not really much law requirements with respect to measurements, but there are other countries, Australia, Canada, US, where the solar parks are much larger. When we go to 50, 100, 150 megawatts solar parks, it's fair to require them to put up measurements. So my question, because we're working with some system operators on this in Canada right now, where they wanted to know which kind of measurements should the solar parks set up. Now I ask myself, is it, where are we in the process to recommend cameras? Is it feasible? Are they reliable? Are there instruments that would be reliable enough to say, and the signal or the processing are at a stage where you could say you could really use it?
Okay, there are a few publications available showing the skill, but in a real application, I would say we need a couple of years more to really, for the technology level that we have a reliable product. It's the same discussion we had yesterday, reliability, and the test or the reliability in a real application has to be proven.
So this is also my suggestion, but I want to add what you said, Corina. We are working in South America, and there they have the same problems. They have power plants larger than 100 megawatt per plant, and they really want to know how the clouds are moving. It's close to the desert, but there are still clouds.
And also I have to say there was no benchmarking yet or comparison of hardware and software. This is planned in another IEA task in maybe one of the next years to have comparison of the different hardware we have available or which was developed, and also the software methods, I think after that we can really see what is the performance, and then maybe in the next step to get standards on that.
Okay, thank you, Thomas. Then we move on to the next presentation from me. Okay. Do we have a handheld microphone? Should work now. Yes. Okay. Sorry for that microphone issues. So we're going to a topic that we've already talked about a bit yesterday and also today. I think it also came up. We made an investigation with our Lidar, and we really wanted to know, so how far can we actually measure with it, right? We wanted to analyze the measurement range in order to have an information for the wind power forecast. And we did this analysis within our forecast project. We already mentioned it yesterday together with ZSW. We had the plan already in 2014. This project started, and the idea really was to, on the one hand, use a LiDAR and use that just to measure the wind speed that would come up, and therefore predict, on the one hand, the output of a wind turbine, and ZSW used the measurement of a cloud camera to predict the solar forecast. That was the basic goal for this project. When we started, we set up the measurement for our LiDAR measurement campaign, and we decided to go into the south of Germany because it was also very close to where we are based, and measure in the Swabian Alps. You can see here a picture of the terrain that we measured in. What you already see there is that it's quite a complex terrain, right? So very different from what we have seen maybe in Hawaii, where you more measured out of the ocean. So this was our measurement site. Why did we use it? We did have a met mask there. You can see it only very barely, and we got some meteorological measurements in that were very useful also for this investigation that I want to show you today. So the question was where to put the LiDAR. And what we knew is that we wanted to go up and get rid of the obstacles and also be more on the hub height level of the wind turbines and even above. So there was this radio tower that we decided to put the LiDAR on, and we just put it here on the top level platform of this radio tower. So we really had unobstructed view for the LiDAR and could perform our investigation. The LiDAR that we choose for this project was a Streamline XR. The product data sheet says it can measure up to 10 kilometers. We have a pulse length of around 410 nanoseconds. What is also important is that we don't have a point measurement, but we have a volume measurement. And with this LiDAR, we can measure simultaneously in up to 167 range gates, as we call them, measurement distances. For this campaign, we decided to go with a horizontal trajectory, which just was focused in the main wind direction, but the LiDAR itself can carry out various trajectories, steering, for example, or vertical scans, whatever you want. So coming back, what actually influences
the forecasting horizon? That was the question at the beginning. And very clear is, on the one hand, the forecasting horizon depends on the wind speed itself, but also on the measurement range, right? And if you want to put it into a table, you can come up with a very simple correlation between the forecasting horizon, the wind speed, and also the measurement distance. And if you believe Taylor's hypothesis, then you can just put numbers to it, as you can see here. So here is, in this table, the wind speed ranging from 4 to 12 meters per second, and our possible measurement distance. And what you can see is, if you want to have like over 20-minute forecasting horizon, then you should really measure like 6 kilometers and more, but that only works for low wind speeds, right? So it depends really what you want. What we see is we really have to have a high measurement distance in order to have a high forecasting horizon. Yeah? So the forecasting horizon depends on the measurement distance. I wrote here, we don't live in an ideal world. So we already expected that our LiDAR wouldn't perform the 10 kilometers that it said in the product data sheet. What we know is that the measurement range depends on several factors. So one factor is the filter algorithm that I apply to my raw data. One other factor is the device parameters, I'll explain later, and also environmental conditions. So it fluctuates, therefore we've seen that already yesterday. So we started with the filter algorithms. What you see here is just a raw data basic sample. Here's the measurement range and just a couple of hours of our radial wind speed data. What you can see nicely here already visually is that, we have some gusts coming in. Then in this case, actually we measured 10 kilometers. Then the measurement range dropped again, but we do have a lot of noise here. And the first task always with LiDAR data is that you actually have to get rid of this noise. So you have to apply your filter data. In order to do that, you get some information from the LiDAR itself. And the information that mostly is used is the so-called carrier-to-noise ratio. And the carrier-to-noise ratio is a value that you get for each measurement point. And it's kind of a signal quality value that you can apply and that you can just put a threshold on. And this is normally done also for, we use it very much for our short-range LiDARs. So you apply a threshold for the CNR, it's called. And what happens if we do that for our long-range data, you see we lose a lot of this data, right? And that's actually very common. So you really, if you apply the CNR value, you throw away a lot of good data. So we had to investigate on how to overcome this, and therefore, develop new filter algorithms. And they were mostly based just on the wind speed itself, actually. So just information from the wind speed, and we were looking for outliers in the wind speed, and came up with a solution that we call wind speed range for now. But what you see is important. So we really can save a lot of good data, and therefore also increase our measurement range again. So we wanted to do now an investigation of our measurement range, and therefore we actually have to know what it is. So we have to put a number to it. What you also see in this plot, though, is that it's not really clear where is the measurement range, because we do still have, also after filtering, quite a bit of noise in the signal. So first of all, we had to come up with a method how to calculate the measurement range, right? We have two methods tried out. What you can see here is the first method, we call the sum range method, an exemplary data set where you just have from one LiDAR beam after filtering, you have valid data and you have not valid data. Those are indicated here in blue and white. And the sum range method now just sums up the measurement range where you actually have a data point. So that's quite easy. In the other method, we call this weighted range method, we wanted actually to take into account that maybe we have some more clusters of data and weight those clusters in a higher fashion. And therefore, if you do this, you take into account where you actually have these block lengths of data, then you see you do get a bit of a difference in the measurement range that you would calculate. So the question now was, which is the better method? And therefore, we applied it to our data. And here you can see a comparison. This is our measurement range for an exemplary data set of a couple of hours. And both methods are applied now. And what you can see is that when we actually have data, both methods are quite the same. So it doesn't really matter very much. However, if we don't have data, and we know that sometimes occurs, this weighted range method that actually takes into account these block lengths and also some data maybe that was not filtered out, this actually still gives you a measurement range. So it's not very robust in that areas where you don't have data. And therefore we decided to trust this sum range method and went with that for the actual calculation. So next step was then to test these the filter parameters we have seen, the device parameters. What do I mean with device parameters? Each LiDAR, if you actually set your trajectory where you want to measure, you can also, in our case, in this, for the streamline LiDAR, you can put up a so-called number of pulses. So this LiDAR sends out pulses and you can determine how many pulses it sends out. For a 200S or for the Lidar devices, it's more called accumulation time that you can set. And what you can see here is we have now statistically analyzed our all measurement data, and we have just averaged over the measurement range. That means all the range gates. How many good data do we have for different number of pulses? And what you can see here is that actually in general, we see, that's the trend, that we get really less good data if you increase for the increasing range gates. That we already knew. What you can also see though, if you have a low number of pulses, these are the 10,000, you get much less data in higher ranges. So there is some kind of optimum, for us at least. We found out that if we have 40,000 pulses, we get the best measurement range. So our maximum range was with 40,000 pulses. What was a bit surprising that we didn't get an improvement if we send out more pulses. That's normally the case. It was not the case for us. Could be that it was set something in the device, or don't really have an explanation for now. But what we can get from this is, for us at our side, if we use these 40,000 pulses, we get a measurement range of 4 kilometers in around 70% of the time. So then the last factor that we wanted to investigate for the influence of the measurement range was the environmental conditions. And we heard yesterday a lot about rain showers that came in and destroyed practically your signal. We had this Met tower there, and what we had different sensors tested in correlation to our measurement range. And here you see the results of the humidity. Because what we found out is really that the humidity has the biggest influence on the measurement range. What you can see here is the relative humidity set into relation to the measurement range. These are 10-minute averages of our data. So it's quite obvious. We have several areas or clusters of our data. So we have here a cluster where we have relatively or really high humidity and a very low measurement range. Then we have a cluster, this kind of a transition area where we have more dispersed humidity and a higher measurement range. And then we have this big cluster. It's actually no real relationship visible. And the measurement ranges between 2 and 5 kilometers. But we can have basically every humidity. So, but what we see is very clearly we only have no visibility, no measurement range if we have very high humidity, right? But not vice versa. So we can also have high humidity and good measurement range. What we said from that, I said that already, or what we deducted from that is that we do have something like cloud or fog formation. And to test that or to analyze this, we have looked at our webcam pictures. So for everyone that sets up LiDAR measurements, I can recommend that. So if you have pictures of your site, you can just see what happens. And what we have done here is just, this is a short video, which I will play in a few seconds. What you can see here is just over the time, our measurement range, which will just change varying depending on how the clouds will move. And I just started, so you can see. So this was a day where we had relatively good measurement range of about 5 kilometers. You see there's quite a bit of cloud action going on the right-hand side. There's some more clouds coming in. There's also a bit of fog coming through, and already the measurement range drops. What we have found out in general is that the measurement range really depends on how far you can see. So the view is really what you get also as a measurement range. So here it clears up a little bit again, so our measurement range also goes up. That's also kind of very well visible. So more cloud action coming in, the range gets a bit better, but now slowly from the back, cloud formation comes in, and our range just drops. Right? Just goes down to 0. We see we have also a bit of humidity. We have some raindrops on our camera there, and you see basically you're blind from there on if you really you're just standing in the clouds. Yeah. Right. So to sum up, what could we conclude? With our LiDAR at this site, we said, okay, we can measure around 4 kilometers with the 40,000 pulses and good weather. Right, so no clouds, no fog. Then the forecasting horizon could be around just 20 minutes. But what we have seen is that this range really is highly very fluctuant and depends on first the filter algorithms, then the device parameters, aka the number of pulses, and mostly for us it was the humidity that has really substantial influence on the measurement range. Open question, and that was very much what Corinna also brought up yesterday. So what for us is actually the optimal condition to measure in? What is the best condition that we can get the best measurement range out? And what is also interesting to us, there are different systems on the market. We have also heard from Neosphere devices. I would like to have a comparison of both. And what we also brought up, we can't, or Peter said it yesterday, we really can't change physics, but maybe we can change the device itself and somehow have a device that measures more robust. So that's it. Thank you for your attention. Any questions?
Yeah, it sounds like a good weather device. What I have learned yesterday also from the comments is that right now we can't change the device. Maybe there are some ideas coming up how to change the device or the methodology, and there is maybe a new device coming up at some stage. But looking at the LiDAR, as we have it right now, whether there are some more differences, what I would be interested in is, okay, we can change it if it rains, if it's strong, heavy weather. we just don't get the measurements. But what are these transition zones? I mean, knowing that something is coming is also something that is important. It's not when it's there so much, but looking a little bit ahead, and then having this robustness. How robust can we get the measurements when we should have them? How reliable can they get when we should have them? And how is the software playing together with the hardware?
Yeah, I think you're right. The interesting part will be the events, when something happens, as we've seen here, when that cloud front comes in, as you have also seen maybe in Hawaii, when the rain showers come in. And how can we detect those? Maybe with our device itself, we could forecast it somehow. If we looked at the range and saw that the range was changing rapidly, we could extract something from that. But I think the solution for the LiDAR itself will maybe also be to think more in somehow in use cases. When is the LiDAR really good? It was somehow like what Mike said yesterday. When is it beneficial to have a LiDAR? And in which cases maybe we have to go to a different sensor and take something else into account?
Yeah, such kind of hybrids. But
yes.
What I'm also thinking about are these different stages of a cold front coming over an area that has different parts of it. If one part of it is not captured by the measurement, maybe we can find out methodologies to say, okay, now we know that if the measurement is not there, that's where we are in the process.
Mm-hmm.
But how is the recovery after such an event? That means when we are behind it, because that would be again something we would be interested from a forecasting perspective, knowing now it's over.
Yeah, that's very true. We have actually not investigated the upwards ramp. There could be
that would be maybe something to look into. Looking into such an event like you showed, and then seeing from which point is the measurement reliable again.
Maybe one point to add is what we found out. This is very highly site specific, right? What happens there. And I think the challenge will be to come up with a method that is more general maybe as well. The fog you probably don't have in every location, and also probably not those fronts coming in through these mountainous region. But yeah, it could be interesting to see when does it, or can we find a method to find also the upward ramp. Mm-hmm.
So I'm curious, you mentioned the product specification was 10 kilometers, and all your analysis reveals it's rarely more than about 4. Right. So, I mean, what are your thoughts on that? Is that purely marketing hype, or under some conditions do you actually get 10? And what are those conditions, and why do you never observe them?
Yeah. So maybe you remember the first raw data plot that I showed here on the second slide or so. So we do measure 10 kilometers at some instances. We don't know what those instances are. That's what I meant. I think I would really like to know what are the best conditions for a LiDAR. And for me, I haven't seen an analysis of this. I think that we have to, or would have to take into account also maybe the particles in the air. So we would have to measure them, for example, and set it into relation. But that's certainly also very interesting for us to see what are the best conditions. When do we really get the 10 kilometers? And apart from that, I can't say more. Yes, they diverge from the product specification quite a bit. Yeah, PJ.
Hello? Yeah. So I think it's the same with many devices. There's a range that is stated on the basis of the capabilities of the data acquisition electronics. You know, as being some kind of maximum that is possible from that point of view. But when you're planning a measurement campaign, that's not the range that you count on. The rule of thumb I apply with a LiDAR is to look at that number and think of half of that number as the basis and that number as the bonus, if you like, when planning a measurement campaign.
Maybe it's a good way to do it, yeah. Mike here. No.
So maybe a centimeter just pointing out horizontally would be nice, because then you would get the backscatter, and also where the cloud is. So that would tell you a lot about what's actually going on with the LiDAR. Of course, the LiDAR is almost providing you with that, but a centimeter does it in a much more detailed way. So that might be an idea, and you could just use a Weissler centimeter, for example, and just point it sideways from the radio tower. Yeah, and then the other idea was something completely different. I think these LiDARs actually pretty suck at doing forecasting, and maybe it's completely the wrong idea. For example, maybe we should just be moving something out to where we want to measure, like a little drone or something.
Yeah,
just a completely different approach.
The solution, or I would really like to see where the LiDAR is good in which cases and where it really is not good, and then compare what are the points that you said is the areas, maybe in the transition in the power curve when it just starts or when it drops out. If these are the really important areas or phases, use cases, let's say, and the LiDAR sucks there, as you say so nicely, then we have to think. Yes.
Yeah, well, that might be nice, but on the other hand, another approach, a parallel approach, could be to think in completely different ways. What techniques, what completely different techniques might actually give us those measurements under these conditions? So not just keep hitting our head against the wall.
Yeah, you're right.
Something. That's just a provocative statement.
Using a drone that flies around then to where you're interested.
Or some drones or something. Oh, you'd be surprised about what.
Yes.
You just need to think out of the box, and that's one way, maybe one way of doing it.
Yeah, but that's, I think, very good conclusion. We have to think out of the box a bit for that. Yes. Okay.
That's a question to the LiDAR specialists. Is there any chance to use a different wavelength that is less attenuated by humidity?
I mean, the whole purpose of choosing that wavelength is the absorption line of humidity, which the aerosols you're scattering off. So I'm not sure that you can really get around that problem, because you need it to be scattered off of the humidity in order to get a signal. I mean, you can increase the emission energy, but then, of course, as Peter mentioned, the eye safety is then an issue. So
I would suggest, there's one more from Thomas. Yeah, go for it. No, I would suggest we really, keep our discussions also for the discussion round now and move on. Yeah.
So now we are going to start with the World Cafe. Therefore, well, the idea is that, I don't know if you know what this World Cafe is, but you have to imagine that we are gonna travel to different continents, and in each continent you are gonna try different coffee and you are gonna try something different. So the idea is that we are gonna split in 4 different groups, namely Lidar, radar, statistical methods, and coupling of measurements with numerical weather prediction models. And I don't know if you have any other idea that you would like to discuss. Maybe now is the time to mention it. Otherwise, we will keep it like that in these groups. So, yes?
Do you mean assimilation or?
Yeah. Like what we discussed yesterday about trying to simulate the numerical weather prediction models. We decided for these 4 different groups, but I don't know if you have any suggestion or you think it will be more interesting to discuss something different. No? Okay, then we will go for that. Ines will be in the LiDAR group, I will be in the radar group, Elliot will be in the statistical methods group, and Gregor will be in the coupling of measurements with numerical weather predictions group. So we will be outside, and the idea is that each person should attend one of these stations for at least 15 minutes. So you should be changing groups, and then the idea is to discuss on what are the barriers of using these methods for different forecasting horizons, like 1 minute, 5 minutes, half an hour, or 1 hour, and to discuss what were these methods best suited for, or what are the limitations and solutions. And yeah, okay. Yeah, so I already said this. Yeah, so that was the end of the presentation, sorry. So we will start right now, and so you can split in different groups. So how many people are we, like 30?
What suggest? Oh God. So the idea is we have 1 group out there and 3 groups out there, and we are your hosts. And you can choose which host you want to visit first, or which continent, right? So I wouldn't actually say 1 group has to go there. You can choose which you want to go first to.
Yeah, but that thing that maybe 5 to 6 people in each group, no?
Yeah, so maybe you have eyes, you can see where there's a very big group. Maybe you can go to a different continent first, and as Peter indicated, you will change anyway. So we think maybe 10 to 15 minutes for each group, and then we swap. We give a signal, and then the groups and the travel begins again, and we will swap the groups. We would like to start now. We have these flip charts, so actually the goal is also to fix something, to write something down, write down the barriers. Now, everything that we've discussed today and also yesterday, write some of that down, find solutions for that. And in the end, afterwards, we want to present it. So the hosts, we're going to wrap it up, what we've discussed, and that will be also a very good outcome, I think, of our workshop, just to have it all in one, on one piece of paper again.
So if you're interested in the NWP coupling to start with, that will be in this room with Gregor, and the other 3 groups will be outside in the small seating areas. See you there.
And if you want to coffee, just grab some and go to your group.
It's a cheap technology in a sense in comparison to flying a helicopter. So what are you writing? What are you saying?
So yeah, so in modeling, integrating models and LiDAR measurements, we not just like to talk about wind speeds and LiDAR, but talk about process. So can you get models that ingest as initial boundary conditions or whatever radial velocities and predict radial velocities? So
what
we can have this.
by radial velocity?
You know the raw measurement of the LiDAR. So you have this measurement of a radial component of the wind velocity vector.
Yeah, but models, numerical models work with velocity vectors.
Yes. So this is what I'm saying. That's a barrier. That's a barrier. That's something to overcome. We get models to ingest radial components of the wind velocity vector relative to the measurement device and output predicted versions of that. So, because I thought one of the key slides we made a little bit in Darmstadt's presentation was just that simple thinking of reconstruction as universal simulation. And that's the way of integrating measurements and models is to use that as how you iterate and converge.
So do you mean to simplify also the signal processing or?
I think the most sophisticated kind of the kind of set up an assimilation scheme which directly uses the LiDAR signal instead of having already diffused wind field. So we can already incorporate it into the
okay, so that's what. Okay.
So there's kind of like that. We've got these direct
like,
measurements
from, and
then we have this kind of intermediate layer between them of wind speed, and then we can just get the direct measurements and
but
models.
I guess that a simulation system would be able to take this in, but it's one measurement out of 500,000.
No, but
that's where the problem. That's where the issue is when you're looking on specific areas where you set up the measurements. That in an assimilation scheme of a numerical weather prediction, a single measurement, even if it's it's in a cone and
they're not a single measurement. There's thousands of measurements of radial velocities from which so you have a scan LiDAR and it's sweeps a beam position through 20 positions and it has 100 range gates over each.
Okay, so you say if you put it up in the sense that it covers an entire wind park, you would have, but still in a numerical weather prediction model, it's only one cell. That's just how it is, and it's not, it is just not affecting the model very much. That's what the
is kind of idea.
So I totally agree, but the thing is, if we would have what I suggested for many years ago, if the wind energy community would agree on that every wind farm in the world would have to have such measurements, then it would impact on the numerical weather prediction models. Because I mean,
should be available also.
And they should be available to, like, we have the World Meteorological Organization. They have a network where aircrafts and meteorological institutions they put all their data in this. You have around 500,000 measurements over 6 hours each day. And if that's the vision. That's what I have said many years ago already.
So is there any progress on that side? Because
I don't think so.
That it's maybe becoming simple model.
But yes, we should put it on again because it's something that I have said. It really then it becomes getting an impact. Yeah. Whether this is med station, masts, all the data that is collected on the wind turbines can only get an effect in the numerical weather prediction models if there is a mass of it. Yes. And then we. So.
But if you do not need only the power output, you also need the
for example, I mean, when they are undisturbed, they are still good. And how many wind turbines do we have in the world?
I mean, that's another line of research there, to use the wind turbines directly in the weather model.
Yeah.
And then you don't need the extra instrumentation.
Yeah, but the extra instrumentation is not something that you can say you don't need anymore because there are local effects that you need on the conversion model, on the power model. So it's not something that you don't need anymore. But if you want to have an influence in the models, this is the only way to go.
Yeah, so if the similar work was done, with the Eveline project in Germany.
Yeah, I have said that at that time.
But they had the problem that estimating the power is the power non-linear business power. So with low wind speed you have low data, with high wind speed you have full load. So this makes also the estimation more complicated. They didn't have their own speed measurements myself.
Yeah, the wind speed measurements from nacelles are not very good because they are disturbed by the rotor and the nacelle itself, so that's not a good solution. But from some turbine data, pitch, rotor speed, and power, with the knowledge of the turbine, you can actually deduct the rotor equivalent wind speed relatively good. That's a line of work that we would like to do.
That's included in the SCADA data?
That's included in the SCADA data. Yes. Depending on whether they use as operators also affected. But we have been developing that data from Vattenfall. 1 second turbine data from wind turbine.
But it sounds like it's kind of a huge effort and a huge community agreement that would be needed in order for this really move forward.
It's like a work
Yeah, it is
in a way. So
but there is one more large issue with it, and we need standards. We need standards on how measurements are set up. We need standards on how measurements are maintained, how they are logged. Because if you just measure, it's not working. I mean, we have this in all our customers where we get meteorological measurements. It's a mess, and we are fighting for it to the measurements, there is requirements for logging, for maintaining, for setting up. They have to report how they are set up, how they have set the offsets, and so on. If you don't have that, if this is not kept in order, the 90% of the data is garbage. And the attenuation models do one thing. We can see this in our own system. They just throw it out. So it's invalid points because they are not calculated. So that's
when you're doing the modeling. So the cell size is typically what? 2.5 kilometers. Yeah. So when your forecast horizon is very short, would you do a faster, do a higher resolution model, specifically just in that volume upwind over those sorts of distances for short-term forecast?
The problem is that the weather is being affected into this box all the time, so you need a much larger box to actually do that. Even though you, we are currently trying to start to think about how really high scale, really high resolution models like LES models or CFD models can do data assimilation from some data in the problem. Again, that's only one point, and you have a lot more points that then are not visualized unless you have a sort of LiDAR wall just in the direction of the.
Yeah, we have, for example, discussed this once in Ireland for many years ago when I was at the university. We said to the energy commissioner that the right thing for Ireland, because they get all the weather from the Atlantic where there is no measurement. So you have over water, you have very sparse measurements. Usually you only have the flights, the aircraft measurements that you get. So the sparseness of the measurements have an impact on the forecast quality of Ireland, and UK is already better because they have Ireland in front of them. And so we said, strictly speaking, Ireland should have LiDARs, radars, and net mass along the west coast all the way up, because this would really improve weather forecasting. And then they said that sounds very nice, but who is going to pay for that? And there was a measurement campaign at the time with I think 15 net mass and 3 LiDARs, and that ran over 3 years, and then there was no funding for it anymore. That's how it works.
But when you have the net mass on the coast, the weather is already affected on the land. Maybe it's too late to measure. You should have measurements. Before.
So floating LiDARs, what floating LiDArs can be sprinkled a few tens of kilometers offshore.
I think it would help already if you would have some LiDARs on the coast that look out on the water. But the Irish Met office is also highly under resourced.
Of course, now with the recent development in satellites, this problem is becoming solved over also to the that data source of this kind of large scale analysis much good. But the information you get from the lower property of the satellite is very weak. You need the perfect roughness of the ocean and just satellite look into other properties very clear.
You can really do surface wisdom on the ocean. That's another option.
From dark, but dark and only one overflight per day.
I would say with more knowledge.
But maybe do currently not more. For
need technology hours, everything hours the most. Yeah, you never get around having local measurements. I think, but it's clear that there is a lot of measurements. There is a lot of instrumentation out in the world that is not used, and one of the things that I find is the worst is that in the wind energy area, it's really only in the resource assessment where there has come up standards, because this is money that the insurances and the finance, the banks want to have. And if the insurances would pressure the projects also more and help the system operators to pull this through in the grid pulls, that if there are measurement requirements, there has to be also requirements for maintenance, etc. I mean, we have had a campaign where we said there were about 40% of the measurements, they were supposed from hub height net masts, and we said that data looks just wrong. It didn't correlate with the forecast. It had very strange outages, and then we said, okay, that has to be investigated. And then we found out that all of those where we had suspicion, they were actually not net mass. They were measurements. And knowing this is one thing, but thinking of you have a met mass undisturbed with the location, and then you realize that 95% of that data is thrown out of our algorithm because the data doesn't seem trustworthy, and you say that doesn't sound like a net mass. And but it has been done because there was no penalty for the operator, and it wasn't looked at. It wasn't. But when the data is needed, you realize that it's garbage. So standardization also of maintenance of instrumentation is something that is highly underestimated.
Maybe we can also frame that question a bit differently. Is there any way to get this like weather prediction or other modeling below the 1 hour range? Lidars, using whatever input there is.
Yes, of course. We have been working with ensemble finance data that can be used on continent. So we look at the distribution of the ensemble members in weather states, and then see where the measurement is, which model has the best forecast for that spot, and then you can bring this forward and on any question. So that's possible.
So you're picking the best model, the best NW.
So we believe in that model that is best at that point in time, and a little bit backwards. So you look at the last 3 measurements plus the one that you have now, and then you get a trend of, and then you can see which of the 75 models has the right weather,
so
which sees the correct weather.
Like a shift in confidence in the models.
Yeah.
Is that changing over time?
Yes, all the time, every time. And then you can use this at any time resolution. You can use this in the time resolution of the measurement. So if you have 5-minute measurements, you can use it on 5 minutes. If you have 1-minute measurements, you use it in 1 minute.
Is that IEA? Right.
knowledge, where you look at a specific point, and if that point fits to that picture, you know that that model has the right, would use the right setup, and then you can use the three-dimensional setup to also look ahead in time. So you can have downstream and upstream information that you can then spread around. For example, you
so in a way, it's like choosing the right run out of a pre-calculated.
Yeah. So the interesting thing about it is that you can have many measurements that feed in, and if some measurements are not valid at one point, it's like a data attenuation, but it's on point basis, and then you use it only on these points. So it's an extremely fast algorithm for a very high resolution temporal resolution that you can simulate, and then also look ahead what happens if that you can see measurements that are taken at a different space. I can see them 2 hours ahead, or half an hour ahead, or 20 minutes ahead, where that weather, what happens with that. So it's a weather-dependent algorithm. So you bring the weather or the three-dimensional component into a single point measurement.
So you use this independent for each point or the other.
Yeah, but you can also then combine it. And the range is that we look on the distribution of the ensemble models or the ensemble members. If they look, let's say, in time, if you have in time the distribution is similar after an hour, you know that you have laminar flow in some kind of way, and your measurement will still be valid, so you can extrapolate what is happening downstream. Whereas if the distribution changes or reverts, you know where you are in a front that's moving or whatever. So you bring this three-dimensional weather component into point measurements of power, for example, or whatever measurement you have that is also part of the numerical model. And that's why we can have this then as wind or direction or power converted, whatever you use, and it's the split second that you need, because if you work with covariance, it's simple mathematics.
Question. So the approach is to use incoming SCADA data and measure it against your models. Do you ever see that you have very correct SCADA data? You have problems somewhere before you receive it?
Yes, I mean, what we do is, because we have 75 models, we have a spread, and if a measurement is outside of the spread, plus sometimes we set a standard deviation on top of the spread, or so that's an experience from measurement. If it's outside of that, it's just discarded, because then you know it's untrustworthy. If it's completely out of, because if you train your model on certain points, they have a certain error range, and then if the ensemble is consistent and has skill on that point because you have calibrated or trained it, then you also know that if the measurement is outside the spread, that's why then you throw it out. That's where we find sometimes where we find that the measurements are not in order. That I don't know whether you remember the Irish the picture that I showed at the end of my presentation with these triangles. That's where we can see if a triangle is always in a wrong color, you know that the measurement is not working. So we often tell our customer that there are some of the measurements that we are getting from.
So I'm interested, what are these 75 different holograms that you have?
Different speeds. So we have different.
You have that in-house.
We have a kernel model, and then we exchange the vertical diffusion and the condensation and the dynamics.
Okay.
And that gives them 5.5. So what else?
Maybe it's time to switch group.
When did we start?
Well before half.
Okay.
I'm still thinking about this, like, what about this data specification of the data things? What the data things are broadly available on the other documented data, so it's not always available if you have very nice summer conditions and you don't get the signal apart from that. Yeah, but
can have these Doppler radars that actually take the atmosphere, right?
Yeah, but I mean, the thing about it, the traditional perspective, then what you have is Doppler bank data, what you can do on devices for purposes of internet. Those data are available already, at least for the moment. So they have quite good correlation of the kind of data available. Radar maybe can be complementary to LiDAR data. What Ines showed, what we're going to close to this measurement station, where the LiDAR was also radar measurement station. We want to look at the radar data also. They when they know the signal to place in the LiDAR, maybe this are the situations where we get signal from the radar. Yes. But we didn't do it about it. We want to do it in the region because we want to allow the data to set up our wind type.
As far as I know, PMI does it. PMI has regular simulate the radar data.
But there are also a couple of applications about FTP. Yeah. The GPU
we had a project, but that was a slightly different type of radar. That was just activity from the clouds and then use motion vectors, and that didn't go so far.
Yeah, you just did the cloud one.
Yeah, no, I mean, when we wrote the project description, we were promised those can do wind. And then we only during the project figured out that they can do wind if we assume that the rain clouds are moving with the wind, and only if there are rain clouds. Then most of the project was sort of still interesting. Not quite what we had.
We are trying now to compare some big images where we're trying to compare example forecasts with the Doppler data wind observations. So then you can actually get better wind observation on a level which is of interest for internet. And then you can see how the Standardization forecast compares to that. Although then you don't have the same problem as kind of you mentioned in the beginning, that you only have the radial wind component, also the model.
What is the megawatts about measurement?
I don't know. It's like it's authorized. It's European data network.
The global.
This must be the global. Yeah, but
what is in WF and NSEP and so on, and those that are
generally the measurements that are VMO measurements.
Yeah, but these are the these are the data observations, and they are
not. That's individual measurements. But the understand what is the grid the next one called. The global one from the
global precipitation pressure temperature.
Normally the GTS, global telecommunication system.
Good, then we move to the
Next, please.
So you are focusing you.
You're the show host here. Ja, ich habe schon gehört, gestern in München Innenstadt waren irgendwie 83 Liter.
Ja, also in Süddeutschland alle jeden zweiten Tag Gewitter und in Stuttgart war eine Woche und der Untersuchung ist abgebrochen. Das war auch so. Eigentlich war ja so 15 Liter in einer Stunde.
Ja, wir hatten hier gerade den einen der trockensten und den sonnenreichsten Monat überhaupt.
Aber das ist ja von Ostsee hoch und jetzt schauen wir die trockene Luft und hier unten kriegen die Feuchte vom Süden feucht warme und dazwischen.
Genau, dafür ist der Trockenheitsindex hier jetzt bei 9, irgendwas von der 10er Skala.
Da ist in Brandenburg McCormick als auch bei 30.
Ja.
whole NWD group, huh?
Oh, they
all left. We have all the problems solved.
I'm not totally sure about this.
But what came out of that?
I don't think it's really amenable to a conclusion as such, but there are several possibilities to use data in forecasting. But if you want to go to this minute scale forecasting, the weather prediction might be good. I mean, there's Corinna's approach, where she sort of has these 75 ensemble numbers,
right,
and then picks the one that's currently best
for the short term,
and then can extrapolate that particular, can claim that that's probably also the one that will hold for the next.
Mm-hmm. Has she done any work on? Is that really true? So if you have 75, you pick the one that's the best by some criteria. Does that really produce the best forecast?
For a shorter period, it seems to be.
That's pretty much, yeah. Okay.
Yes. She published a few papers a few years ago on this one.
Yeah. Yeah, it's pretty well.
It seems to work. I couldn't get my head around it at the time, but.
Well, I wonder how does it compare to persistence or something really simple. I mean, normally
no, because
the emission.
It's like
you adjust it.
Picking out of a precompiled weather database.
The one that matches.
The one that which is the development in which is closest to the last 3 measurement points.
Okay. It's following a similar trend to what was observed.
Yeah.
You receive level.
Yeah. That's where that might come in.
Yeah. But how do you bring about, if you have other information, SCADA data or Lidar or whatever, now what's the approach would be then? You put that forecast and the other data into some machine learning algorithm and it binds it in some way, so now you have an NWP input and then you have the other data inputs. Has anybody tried that?
I think that's a quite logical step. I mean, there you get one model output,
right,
and then usually some sort of machine learning approach will give you the result.
Right. Yeah, I would think so. Has anybody tried to do that? Where you merge the current data and an NWP, like from Corinna's method, into a composite algorithm?
I don't know what they are doing afterwards.
Yeah.
So probably she's doing something like that.
Something like that. Yeah.
It's not standard industry practice also because not many people have a 75 lambda ensemble right at this point.
No, that's true. Although, I mean, everybody has a number of NWP solutions.
Yeah.
As you have a number of providers, so yeah. Yeah. So, I mean, it's not exactly the same thing, but you still have some options.
Yeah. Another possibility, one thing we asked about or discussed slightly was is anyone using radars for data estimation? I think EMI is actually doing it operatively.
Well, the HER, of course, does. HER in the US, they use radar data. They assimilate. But they update every hour. Because one of the primary applications of HER is convective forecasting for aviation. I mean, that's why it was really developed.
Okay.
And so they do a lot of radar data assimilation. And you can see it in the forecast. I mean, you have a well-defined system of radar, it regulates it right up.
Yeah.
Now, the evolution of it may not be right, but it'll be there.
Yeah. Okay, cool.
Yeah. Yeah. And actually, in ERCOT, we've seen a number of cases where the HER actually forecasted the outflow boundary of the thunderstorm that went through a wind farm.
and the forecast is amazing. Now, most of the time you'll have amplitude error, phase error, but sometimes they get it right. When they initialize the radar data, you get the connection in the right place, and you get outflow measurement in the right place to one part, and it's an awesome forecast of the ramp up of the outflow connection. Okay. I mean, so it's possible, but you have to get everything right.
Yeah, and it's also along the horizon. I mean, for the purpose of this workshop.
Well, yeah, minutes, no.
Minutes.
In a HER, it takes an hour. An hour on the cycle, it's almost a full hour to run the forecast. And then there's a little while of dissemination of the data. You're talking hour 15, hour 30 before you can actually use it. So that's a lot of time, you know, when you look at that convective system. So, I mean, but yeah, you run your own system. It would be hard. I mean, it's possible. You can get radar data, right? And you can assimilate it. You know, and HER is worth basically. And so you can emulate what they're doing over a small area and run it faster, right? Compared to a small area for a 1 hour forecast, say, you can probably do it in 10 or 15 minutes. And you still lose a piece of time, but then you would have maybe a 30-minute forecast or 45 minutes.
Yeah. If you have a continuous running thing that you just nudge or something, becomes available.
Yeah, no, that's probably what you would do. I mean, you would run it continuously. You would do data assimilation continuously with every radar cycle, and then periodically you would spin up a forecast, right, for an hour or two. I mean, you could set up that type of system. You probably could do it on a cluster, you know, with a couple hundred cores or that type of thing, which is not that expensive now. And, yeah, if it was important to you, you could do it.
Yeah.
I don't know that anybody has done it, but I think the limit would be probably 15, 20 minutes. You know, Empire has done a lot of experimentation with that type of setup. I mean, they don't do any real-time forecasting with it, but has anybody tried to assimilate live radar?
Not that I know of. I think that was very bad. It sounds relatively obvious.
You might do it. I mean, yeah, certainly the 3D bar you could do it.
Yeah, and you probably don't need new operators because it's sort of just an agnostic.
Yeah.
For other purposes. Yeah.
Yeah, I mean, if you don't, I don't know what impact. I mean, the volume of data is small, right, compared to the NWB volume.
Yeah, exactly. So that's another point that we had here, that we already used 500,000 observations from around the globe.
Right.
So one more has a very local effect.
Mm-hmm. Now you might have more effect if you do a continuous 4D assimilation, you know, every LiDAR cycle, because, you know, then you're effectively increasing the volume of the data because that data propagates out. If you do it one time in a 3D bar, you probably have very minimal impact. But, you know, LiDAR produces data every few minutes, right? So if you assimilate it in a continuous continuous data assimilation cycle, then that's really a fairly large volume of data eventually. When you do it over an hour or 2 hours, then you kind of fill up a volume.
Yeah, what Elliot was showing was
49
seconds for a scan.
Yeah. Yeah.
So to use that, you would need 40 watt. Because otherwise, the forward all that time.
Right. Yeah, if you're doing it at one time, yeah, you're losing a lot of information probably a little more time.
Yeah. A 40 bar is pretty heavy.
Pretty heavy. Now, it wouldn't have to be the 40 bar. It could be like a Newtonian relaxation, which is not as computationally intensive. Yeah, it's probably not as effective either. But you can do that. Yeah. But it would be interesting to see a comparison of that type of MWP approach versus the machine learning type approach where you don't use any MWP. Now, the ultimate solution might be, probably is, you integrate everything, right? Some MWP information, the Lidar information, the SCADA information. So, but it would be interesting what the relative value of an NWP system like that, assimilating the data versus a machine learning, where it's simpler to find the signal, but you don't get interaction of it, right? There's a lot of just relationships between the signal and the response.
Yeah, and also because one of the things that Lidar had Peter actually was if we make a netmask / Lidar part of the grid connection demands and feeding that into the operator, would that help or would we need upstream?
We need to provide the weather information to the operator. I don't know. I mean, that would rely on their ability to interpret it, right? Yeah, I don't know. It's highly variable.
They would have to hand it on to the weather service.
Yeah.
Or run their own weather module.
Yeah.
They would run that job.
Right. No. Now, in Europe, is the wind farm data provided to the weather services? No. For input? No. Now, it's like HER actually does incorporate some wind farm data. They have agreements, the National Weather Service in the U.S., with certain companies like Iberdrola, Nextdoor, I think, and the wind farm net data actually flows into the AWS, and they use it into HER. Now, not every wind farm, because it depends on the agreement.
That's just the net data, right?
Only the net data. But it's by agreement with each company, so it's very sporadic, which farms.
These refresh models are the best short time scales.
Yes. Now, HER does a very good job of assimilating various types of data. The short-term forecast is pretty good. I mean, it's limited in some ways, but yeah.
What's the horizontal resolution of the HER? 3 times. Yeah. Probably could nest your own system there if you
Well, that's probably what I would do if we were to do something like that. Use the her as initial and boundary conditions, estimate within that, and then assimilate whatever additional information you have. That higher resolution.
That'd be a nice research project.
Yep. Yep. No, I would do that if I have the time for people to do it. No, it definitely might have value.
Yeah. And the data.
And the data.
Because ideally you would have something like a cluster of wind farms. Like
per cap. Yeah, I mean, you look there, I mean, there's a lot of wind farms. So you assimilate that data, you assimilate the radar data at high resolution. You can do 500 meters even over a small area. And you might be able to forecast, some of the boundaries, the outflow boundaries, cold front boundaries, very precisely.
Yeah. And then probably all that high resolution information would be washed out after a few hours anyway. So you don't need to go.
Yeah, you wouldn't go out more than maybe 3 hours, maybe not even that. Because then you go back to the her solution anyhow, right?
Yeah.
Because the boundary conditions will dominate eventually.
Yeah. That also would keep the running time relatively low. I mean, you still need to load all the feeds, which is probably a major effort. To get the feeds from her and then load the feeds and start to do that. So that's all quite some.
Well, you could, and we've done this, you could use the her 1 hour forecast as your starting point. Which is usually pretty good.
Yeah.
And then you use whatever other data you have to modify that, so you have a head start. Otherwise, you have to wait for the new her analysis, which will delay you.
Yeah.
So you use the 1 hour old her, and then you run from there. Now, there's, in Europe, you have 3 hour updates, Germany, something, 3 hours.
I think Germany is the only one.
But it's nothing similar to that, right?
Well, no, DMI has some refresh model now.
Hour type scale.
I'm not totally sure. I mean, we had a research project proposal
that
we put in 7 times, and now we got it back. No, this is not going to be.
Not going to happen.
7 times and 2 different funding organizations.
All the effort for nothing.
Indeed. I mean, the last few times the effort was gradually
Yeah.
But then you had to reform and rewrite the thing that was reform.
Yeah, that's the way it works, though. I've been there. Many iterations and nothing comes of it.
Yeah.
Yeah, I think it's worth some experimentation to see what can be done with that.
Yeah. Because a very short term.
Because computing power is getting cheaper, right? Less expensive. So whatever you can do now in a couple of years, you can do more easily.
Yeah, I mean, that's old computer. I mean, they say they could have a very high resolution work run in hours.
Yeah. In 2 or 3 years, more power, lower cost.
Exactly.
Yeah, I think it's a feasible idea if you have enough volume of data, right? Well, I mean, that's going to be a problem. If you put in one profile, it's not going to matter much. Probably not worth doing. Maybe you can do 4D data simulation of some type, or use multiple data sources a number of wind farms. So I think you have a LiDAR, you have all the wind farm data, maybe some other sources.
That might actually be a thing to do with doing WFIP.
Yeah, that would be. Well, and they've done, they tend to do longer time horizons. I mean, WFIPs have always been long intraday, and then day ahead, right? So this 0 to 2 hour doesn't get worked up very much. And even the HER, because the time frame that it's optimal for is probably 2 to 6 hours out as well, right? And then with the other GFS and so forth. So that tends to be what people do. And then under 2 hours, people don't look at the NWP that much. For a 1 hour forecast because you have all the delays and the resolution issues and all that. So WFIPs tend not to go that way. So normally they show how much they improved for her 3 hours out.
Yeah.
So,
what's the test for the doctor?
Well, it depends on the application. So, I mean, that's not good enough for most of the ISOs in the US. I mean, they're all doing 5 or 10 minutes, 15 minute forecasts. Real time markets. They all have that time frame where it's under an hour.
Yeah, under an hour is already hard to get to that forecast.
Well, you see, under an hour, say with the HER, is really no different than about 2 or 3 hours. We have a 3 hour forecast, and there's probably nothing in the HER that's going to give you more information an hour later. I mean, maybe it's a little adjustment, but you will get a departure. You will have real time information.
Does the HER also have this startup HER?
Not so much. They simulate a lot of data in a 1 hour cycle, right? And so, and they've done a lot of work to assimilate all these different high frequency data sources. So the spin up is minimal. I mean, there's a little bit, no doubt, but not too much. It's pretty smooth. And they run a continuous data simulation.
Yeah, exactly.
So it's not a 6 hour thing.
Continuous analysis.
Yeah. Right. And then they spin off the forecast every hour.
So that's not much.
No, it's not a lot. It's all about shape. Now the HER is really improved. The first year it was out, it had a lot of problems. It was not really usable in many situations. But now it's pretty good. I mean, whenever I want to have a short-term forecast, like 2 to 6, 7 hours out, I go to the HER first.
Yeah.
I look at that, and what's the pattern? And then, go from there, whatever information you have beyond that. But it's a really good first guess. You want to look at what's going to happen for any parameter. Wind, rain, whatever you're interested in. It'll give you a pretty good idea what the trend will be. Now we know a little bit more than that, but
different timescale. What's the weather going to be next weekend in St. Paul?
A good question. I haven't even looked. Yeah, I don't know. I'm so busy traveling and doing things around. It's been warm in the middle of the country, so I don't know if that's they've had a lot of warm air go north into the upper Midwest. But there's been that ridge in the middle of the country, the trough has been in the east. New York area has been wet and cold. We never get rid of the clouds. It's always cool and miserable in May and June. Everybody's complaining there.
Yeah, he was actually May was the sunniest month since the beginning of observations.
Yeah. Wow.
360 sunshine hours.
Yeah. Wow.
Yeah. That's 11 and a half hours on average per day.
day, yeah.
But in my maps,
amazing, right? Yeah. Yeah.
Tunes, not really much else. I mean, you can see that that's not a typical summer color for the niche grass.
Yeah,
the brown
is brown. Yeah, yeah. Yeah. It's like Albany in the summer, but I mean, we are so green right now. Plus it's so cool and wet. Thick green. It's amazing. And normally in Albany, in June, July, it dries out a little bit. So you get that type of color. That's for sure.
Southern Germany had thunderstorms quite a lot now, and water on the streets and
really?
Yeah, I mean central Munich, even we get yesterday alone got 83 millimeters.
Really? Wow. Heavy downpour.
A few kilometers away it was nothing, next to nothing. That's because they had very little movement.
Okay, yeah.
You get one entire thunderstorm cloud.
Yeah, over one area, one location.
Staying in one area, just empty.
That's a lot of water, yeah. And I know in the U.S. when that happens, there's certain areas where you get flooding. I mean, it's really enormous because it channels into the basins, the narrower valleys.
Yeah.
And they get an enormous amount of water coming through that basin. Not good. Yeah. So yeah, sorry, I don't know. I'll have to look myself. But normally this time of year, it's pretty warm up there. You know?
That's what
you never know because you could get a cold outbreak, cold air mass move in, but most of the time it's pretty warm. Did I mention to you, Aiden? Mentioned you were going to need 5 minutes.
Yeah.
So we'll reserve that additional time then for the discussion, or if you need it. Have a few more minutes. Are you checking Minneapolis weather?
Yeah, whatever PMI says, but PMI is just essentially the same what it says. Looks like
the full drop
20 to 34.
Not bad.
No,
11:30, I think, right? By the program. They're supposed to be back to work. Well, sounds like a pretty good summer. Yeah. Good. Maybe I'll check with the other two groups there and see.
Did you guess? It was in browser.
All right. So, thank you very much. I think that were very fruitful discussion in our World Cafe. As you see, we've just put up our results on the post-it notes, and well, what would be the next few minutes is that we just go through and summarize what we've discussed with you, maybe also come up with some more points. And I think then we can very nicely close up also our workshop, but let's do the results first. Do you want to start with radar? Yes.
Okay, for the radar, we not only focus on the Doppler radar, but mostly what we agree is that, first of all, we don't know what we are backscattering. So this is something that which should be further investigated. And the main problems are in offshore conditions, and where the availability is quite lower. And apart from that, another barrier is this high cost of the radar. Also the availability, as I said, and sometimes that you are not measuring the range, or you don't have the availability at the range that is of your interest. And also one of the interesting points is that we think that there is a lack of the big view. So how we should use these radars. So we are talking about different technologies, but we need someone who has this big picture and knows what we should investigate. And also there is a lack of maybe communication in research institutions, and also this increasing this communication could also attract more investment for this system. So a solution or things or focus where we think that the radar will be interesting, we agree that maybe radar will be more interesting for detecting ramp events, and also there are other type of radars like marine radars or high frequency radars that could be also used for that. We also thought that it would be very interesting to use the measurements to design or to use them as a reference cases for other type of analysis. So kind of lessons learned from the use of this Doppler radar. And well, where else? Yeah, we also talk about the fact that we need to learn how to work with uncertainty. That sometimes we don't have measurements, but maybe if we don't have measurements, we know that we have high uncertainty, and this is where it is. So we cannot change that, and we need to identify those situations. And just final point, yeah, there were also some crazy ideas like using bears, putting some kind of detection on the bears so that we could follow them and get the signal, maybe for detection of storms when the bears are coming back, or yeah, different things. And yeah, so but as a summary, I think what we decided is that radar will be more suitable for ramp events or cold fronts or complicated situations to be forecast, and that there is a lack of finding what is the important point to be researched. Yeah, that's all.
Okay, thank you. Are there any comments to that? Nice summary. Okay, then I'll continue with the LiDAR group. And we have also thought of the barriers, and we tried to find solutions for the barriers. And the first barrier that we came up is what we've talked about already a lot. We do have a very fluctuating measurement range. Therefore, yeah, the question of availability is there, very big actually, of our forecast, therefore. So that's a very big issue that we have with the LiDAR itself. Solution would be we need a plan B. So first of all, actually, we need to find out what are the use cases where it's actually really a problem if the availability is not there, and then we probably need a plan B. And what we thought of is that for example, we have to take different sensors into account. Maybe we have to combine it with the radar measurement. There was, I think, Mike, it was that we use drones, for example, or could we even come up with a measurement sensor network? So we need alternatives, or at least we need to think them through and go through all the alternatives and ideas that we have for the plan B. So that was one issue. Then not only availability is important, that means do we have data because of the range, also the reliability is important. We haven't talked much about that yet in the big group. So does the LiDAR work itself? Does it function? And along with that goes, do we need to have maintenance on the LiDAR itself? There's no clear recommendation at the moment yet. How often do I actually have to go out and wipe the lens of my LiDAR maybe? Or do I have to change maybe some mechanical parts or so? So that's the reliability part. The question is a bit, will the LiDAR work or when will it break, and what is the maintenance schedule? And a solution for that is that we need something like recommended practices. So recommended practices that tell us maybe also really application specific for forecasting. What should be the maintenance issue or the maintenance schedule? Also, what is maybe the quality control that we have to apply to the data? That is not really clear yet. Can we actually use the data for the forecast that comes in an online form? So recommended practices would be good. Another barrier that we saw is that, okay, we say maybe we can use a LiDAR, but how do we use the LiDAR for the forecasting? So that means, how do we set up the measurement campaign? Do we take one LiDAR? How many LiDARs do we need? If we have a huge wind farm of maybe spread over 100 kilometers or so, maybe we need to take 5 to 10 LiDARs or so. We don't know that exactly yet. We also don't know where to put them. So can we, in onshore cases, put them on the ground? Do we have to put them up on a nacelle? Can we, in offshore conditions, maybe put them on this transition piece? Or is it better also to put it on the nacelle? Do we maybe need floating LiDARs we talked about briefly? Could also be an option. So the really question here is, how do we set up this measurement campaign of the LiDAR? So the solution for that would be that we really also need to investigate a bit more and come up with different use cases maybe as well. For what do we actually, or for what purpose do we use the LiDAR within forecasting? Where is it really beneficial? And how do we need to measure then? So what's the measurement strategy, for example? That also goes along with the recommended practices that I've already mentioned. So maybe that could be, in the long run, really summed up somewhere in the recommended practices. What else did we have? Maybe in terms of the horizon in which we want to forecast. That is a definite barrier. We're talking about barriers again of the LiDAR. So when we use LiDAR for the forecasting, we're talking about minute forecasting, right? Maybe up to 30 minutes, we said. That was a guess at the moment. It definitely becomes difficult to use a LiDAR for the hour forecast because we don't have data there. And there again, we need something like a plan B. So we need an additional forecasting method, maybe different sensor, but also definitely a coupling maybe with numerical weather prediction models. Another point, if you decided you want to use a LiDAR for your forecasting, a barrier is then, what do you actually do with the data? So what is the data processing that needs to be applied to the LiDAR? So that can be a barrier if you don't really know what to do. The solution for that would be that on the one hand, you ask, first step, the supplier of your LiDAR, right? Please support me. What should I do with the data? That would definitely help. And it would also help if you actually have access to all the information of your LiDAR measurement campaign. That means if you get the raw data of your LiDAR, and then you can process that in the right way. So that means we don't want so-called black box measurement campaigns where you just get some data and you don't actually know where it comes from or how it was processed, and then it's really not very usable. So that is an issue. Maybe also the last barrier that we came up with is, to us, it's not really clear yet, what do we really need from the LiDAR? How should we measure in terms of what are the parameters? Do we need a better wind direction forecast? And also, how do we couple, or how do we then assimilate our LiDARs into maybe a numerical weather prediction model? What do the modelers need from us? So it's a vice versa, right? So what's the measurement strategy in terms of really the coupling with other sensors or also other models? And what we have come up there with a solution is that we need to sit down together and discuss a bit more and talk, actually. I think that's a very very common thing that always goes a bit wrong, that the measurement people are doing what they want and the modelers are doing what they want, but we need to have a better exchange there and really see how we can solve the problem together, I think. Yes, I think that's a good summary. Gregor? Then we come up next, Gregor's group.
This is going to be quick because we had one initial group that was really productive, and then we had another mini group that also was very productive. Anyway, one of the things that's really important to notice about numerical weather prediction is that globally there are about 500,000 data points every 6 hours available, and they drive the large-scale numerical weather predictions. And so any single data point is going to have a very limited influence on the models. Having said that, one of the possibilities that we came up with to get to the, say, 1 or 2 hour range might be to use one of these high resolution rapid refresh models, like the US HER or similar models. Take the 1 hour forecast, initialize a localized version of the HER with that as boundary conditions, and then assimilate whatever data there is in a more continuous cycle with some sort of a 4D data assimilation. So that takes the timing into account as well, that makes use of the high frequency of the data, and that with that kind of setup you might get new forecasts for the next, say, up to 3 hours in 10-minute installments, 5-minute, whatever you really want to write out of the model. From about 20 minutes after real time. So you have that period where you have to run the model. That's a given, and even with really big computers, you probably still use a quarter or 20 minutes or so to also run a local model. Another idea was to not have the wind model separate in that then converts the LiDAR raw output to the wind field first, but to use the NWP model directly, so to assimilate the raw model, raw measurements of the LiDAR in the NWP model directly. That might give some improvement. And then we went over to whether a rain radar could actually be useful, and there are some using it. DMI, I know, does it, and the HER does it. We also had a project with marine radars in the Radar at Sea project here some years ago, but that didn't go exactly where we thought it would. And finally, one completely different approach was the one by Corinna, and because she is having these 75 different ensemble members pre-calculated, and just uses the last 3 measurements to pick the one that's currently seemingly giving the best trend. And there seems to be some possibility to make use of the measurements in a slightly different way instead of using data assimilation and starting the models with them. So for minute scale, numerical weather prediction is probably not the answer.
Great wrap up. Any comments on what Gregor said or the previous? Nope. Okay. Oh yes. Come in. 1 second.
I don't know whether I didn't hear it, but I think the measurement net that we were talking about is something that should be spread around in the community, that if the wind energy community or the renewables community would have something similar like the meteorological community, a global network of data that is collected at a central platform or data center, and then accessible to everybody that is doing kind of work and can make use of this data. We would have thousands, 100,000s of measurements from turbines all over the world. And that could also be something that would help the numerical models on a global scale, but it can help in many ways. So maybe this is, I have proposed this for 5 years ago, I think at the UVIC forecasting workshop, where we were asked, what would you do if you were king or queen for a day? And I said, that's what I would do. I would order every wind turbine to send the data into a data hub. So I think that should be spread around.
Yeah, actually what I mentioned to say was that John alerted me to the fact that at least Iberdrola and maybe other developers in the US sell their data or send their data to NOAA as input for the HER. So some of that is already happening.
Okay, so my group was focused on the statistical methods of doing the forecasts. We kind of went off on a lot of tangents, which I found very interesting. I'll try to condense that down. So we talked a lot about leveraging the existing data and not having to purchase and install and maintain new instruments, which can be quite a cost commitment, as well as reliability concerns about new instruments. If things have been working in the past, you know that they work and we can use this data. So a lot of it was discussing what kind of inputs we have, and that this is a large volume of information. We need to do some feature engineering to see what's actually relevant and collect this data on very high frequency. A lot of it is recorded, and the sensors are actually measuring at 25 or 50 hertz, but this is a lot of times averaged, and even though it's saved, it's discarded once it's averaged into, for example, 10-minute periods. So we talked about some new types of data that could be used besides just the wind speed and general meteorological information. Active power from the wind turbine itself, also looking at entire wind farms and doing clusters of wind farms in different geographic areas. This information can be a smooth signal, which is a high predictor for the future, especially upstream wind farms, for example. We talked about looking at data from the power system itself, like reactive power and voltage faults. Now this can be collected at the transmission connection point between the wind farm and the grid, and can give a lot of information about the future. So we talked about also issues with the data, for example, that we spend a lot of time on filtering it and determining, basically shaping the data into a method that we can use it. A lot of the time series modeling approaches require, for example, stationarity, that you have a mean of 0 and a variance of 1, for example, no trends in this. So one method that you can use is looking at the changes in the magnitude instead of the actual value itself. So you do differencing, which is a common method in this ARIMA models, the autoregressive integrated moving average models. And we talked also about, let's see, yeah, what is the goal? You have to define your metric here. If you want to have a system that is optimized for minimizing a mean squared error, for example, you'll get just the average errors to be low. But if you design your metric and your weighting of these errors for example, rare events, then you can actually have a system which is kind of designed for your application, which is very important here, how you set up the input data and what you're actually trying to minimize. We also recommend that we try to do some standardization of the data streams. For example, some data loggers will put a value of 0 if it has a sensor error, and this can actually be considered, is it actually measuring 0 or is that an error? So this is something that, yeah, the instrumentation we can work on, and from the data processing side. Also, issues in data, for example, with curtailment and maintenance scheduling, which is not always communicated in the data that you're feeding into your models. So, for example, if you use active power signal from the turbine and you don't combine that with the indication of curtailment or downregulation, then this can actually build an incorrect model. So if you have a wind speed and a active power which is lower than what it should be producing, then your model will actually predict this curtailed condition, which is wrong. So this is quite difficult to kind of put into context. Let's see.
On a side note, don't be alarmed about the nuclear alarm.
Yeah. So another. Hello. Is this one working?
No. Did they shut down the power?
Test. I'm out. I guess that's the end of my
Take one of those.
Test. Okay. As Karina mentioned, perhaps a top-down approach from the central TSO, who's actually in the end responsible for making sure that the system is balanced, of kind of requiring data reporting between the turbine and wind farm operators and the forecasters who can use this data, as well as the system operator itself. For example, in Ireland, where they can send direct messages and signals to downregulate and shut down, and yeah, for example, to the turbines themselves. This is something that we can move towards. And yeah, of course, this depends a lot on the country and the grid code and the level of wind power in the system. But yeah, I think that pretty well covers our discussion, at least the important parts. So we'll post photos of these that you can read more later if you're interested.
Okay, well, thank you very much, everyone. I think that was a very nice wrap-up of all the issues that we've talked about in the last 1.5 days and all the barriers that we found. And also, I think it was nice to see that we did come up with ideas for solution for those barriers. And that I think we still have a lot to do and a lot to research on. We're almost at the end of our workshop. What I wanted to come up finally was with the slide that I showed yesterday morning, the expected outcome, just so you know, yeah, that we maybe have something tangible. So I think what we definitely have achieved is that we have an exchange of experience carried out in the last 1.5 days. We definitely have created links here between everybody that works on the same topic and between end users and researchers. This, as Ayat has said, our results here, we will definitely put them into the proceedings. So what we want to come up is with a list of barriers, and we will have that, and also possible solutions, so that is great. Now the question is, maybe we can come up with a paper. And the question always is a bit, who would start with something like that? I think we have to talk again internally. Would maybe somebody, quick response, be interested in contributing to a paper about short-term forecasting, or as a result of this workshop? Maybe quick hands up. So we have okay, it's good. It's already a handful of people, definitely. And I think the solution there could be that we, after this meeting, just send a message around and an invitation and come up with an idea for a paper. So that would be a very nice outcome, I think. Yes, and as already said, the proceedings will be there. So I think you will just send around a link afterwards to an online, I don't know how you do it in Task 36, probably on the homepage, or we just send around a mail. I think you'll definitely hear from us. So
and the YouTube as well.
Right, and the YouTube video, it's true. Yeah. Huh.
That's on it's on the IEA Task 36 channel on YouTube, and I will send a message, thanking everyone, and also link to that.
The Google search term is IEA Wind Forecasting.
Yeah, go for it.
No, because there is a special issue from the Energies journal for, I think it's very short-term forecasting or short-term forecasting, but the deadline is 31st of August, so it's quite tight. Okay. But maybe it will be a very good opportunity, because I think it will fit very well on the topic.
Yeah, what paper?
Yeah. Energies, a special issue on, I don't know if it's short-term forecasting or very short-term forecasting, I think.
Okay, I think then we can discuss that and just get back to everyone, and the interested parties can say we want to write something. Okay, any last comments from your audience? Any feedback maybe as well? Can also come up later. If that's not the case, then thank you very much again for coming. Thank you to our hosts. I think Gregor and Elliot have organized the most here at this site, so thank you very much for that. And thank you all for coming again, and we hope you have enjoyed this workshop and took something home, and have safe travels back home.
Yeah.
Thank you.
And I want to thank Ines and Laura and David, of course, to actually mostly do the scientific part of the workshop, and to get the good introductions and hosting. So let's give them a hand too. And then I'd like to ask if anyone was yesterday at the dinner and forgot to pay, I'd like to talk to you.
Oh my God.
Having said that, there's lunch outside, and the next things, I guess, are the next week, the meeting of the IEA Task 36 in St. Paul. Then in September, the workshop at Gentofte here at Ørsted on loads and control of Task 32. And the rest will be available from the mailing list. Thank you.
Thank you.
Oh yeah, I think that went good.
I'm gonna take the deadline for this special issue because the remote sensing was extended like 5 months, so I think I can contact them, and maybe 31st of September will be more. Yeah, I can check it here.
I need to supervise this Lidar exercise for the summer school.
Yeah, you have to go. Do you go to work? Then when I don't know when I will
be in Brussels though at the
beach is when
yeah.
But maybe we have talked or can talk again this afternoon.
Yeah, I'll just be gone 1 hour.
Yeah, fine.
So if you guys
Just
hang
stick
around,
around. We have lunch now.
if you need a place to work, we can need a desk or something.
Do you want to take those, or should we keep them just for reference? Because I mean, we're sending the pictures out there.
Yeah, I took the photos.
You took the photos of everything?
But maybe keep them just for.
I would also keep them. So if you could keep them here, that would be easier. I don't have to schlep them to Stuttgart.
Are they auf dem Anfang?
So that's why he's got to track
Solar, it's called solar and wind energy forecasting. It's called solar and wind energy forecasting.
Okay.
So I think it's I mean, if I would have had this at the beginning of the PhD, it would have given me pretty nice, isn't it? Cool.
But isn't that typical that this is at the end of the PhD?
Yeah, I mean.
But it's not the end of your PhD, it's the beginning of your postdoc.
Okay.
Of the rest of your career.
Yeah. Let's see.
I mean, this to work on all those issues should keep you busy for the next 10, 15 years.
Yeah, you think so?
Yeah, and then something else happens.
And we start doing nuclear.
By the way, do you have opportunities on postdocs now?
Not like.
Or maybe Pierre can start?
It's,
But I wanted to talk to him because of what I presented yesterday is very related to.
I mean, it's always useful to talk to Pierre.
Yeah.
He also seems to be equipped a bit better with money than I am.
Anyway,
and for forecasting, I don't have anything right now, but I mean, from the Lidar angle, that's also.
I want to talk to Mike as well.